Imagine you're strapped into a seat the size of a large armchair. Around you, 3 other human beings are breathing the same recycled air, feeling the same vibration in their bones, staring at the same instrument panels glowing in the dark. You're not in a theatre. You're not watching a simulation. You're 400,000 kilometers from home, and in approximately 90 minutes, you're going to slam into the Earth's atmosphere at 25,000 miles per hour. The temperature outside your window will reach 10,000 degrees Celsius. That is, for context, roughly twice the surface temperature of the sun. Your survival depends on a 3-inch thick shield made of a material called avcoat, a shield that, during its last test, cracked in ways that nobody predicted, shed chunks that nobody expected, and behaved in ways that the best computer models on the planet could not explain, and there is nothing you can do about it. You cannot open a hatch, you cannot eject, you cannot call for help, because for 4 to 6 of those 7 minutes, every radio signal between you and the rest of humanity is physically blocked by a sheath of superheated plasma wrapped around your capsule like a cocoon of fire. You are, in the most literal sense, alone. I'm Christopher, and you're watching This is Space. Join me as we dive into the 7 minutes during Artemis II that have engineers losing sleep, veterans of the Apollo era raising alarms, and 4 of the bravest human beings alive choosing to climb inside anyway. This is not a story about failure. It is a story about the razor's edge between survival and catastrophe, and about what it means to look at that edge and take one more step forward. Let us start from the very beginning, because to understand why these 7 minutes are so dangerous, you first need to understand just how extraordinary the journey leading up to them actually is. The Space Launch System rocket, the most powerful rocket ever built by NASA, generates 8.8 million pounds of thrust at liftoff. 8.8 million pounds. To put that in perspective, it produces more thrust than the Saturn V rocket that sent humans to the moon during Apollo. The rocket climbs through a phenomenon called max Q, the point of maximum aerodynamic pressure, where the structure of the vehicle is being squeezed and bent and hammered by the combined forces of its own acceleration and the density of the atmosphere it is punching through. Our engineers deliberately throttle the engines back during this window, sometimes to 65 or 70% of maximum thrust, just to prevent the rocket from tearing itself apart. That moment, that deliberate hesitation in the heart of a machine producing millions of pounds of force, tells you everything you need to know about how seriously NASA takes the forces involved. But the rocket survives max Q. The capsule separates from the upper stage on schedule. The crew floats into lunar space, weightless, conducting checks, testing systems, and for a brief, extraordinary window of time, they are part of an exclusive club of human beings who have travelled further from Earth than almost anyone in history. And then, inevitably, they have to come home, and that is where everything gets terrifying. Before we talk about the physics, before we talk about plasma and parachutes and pressure suits, we need to talk about the 4 people inside that capsule, because this story is not abstract. These are not test dummies. These are not characters in a screenplay. They are real human beings who wake up in the morning, who have people who love them, who have careers built on decades of discipline and sacrifice, and who made a decision, with full knowledge of the risks, to sit in that chair. Commander Reed Wiseman is a US Navy test pilot and NASA astronaut who has already spent time aboard the International Space Station. He knows what weightlessness does to the human body over extended periods. He knows what it means to look out a window and see nothing but the curvature of the Earth below you and the infinite black above. Pilot Victor Glover is equally remarkable. A naval aviator and NASA astronaut who became the first black astronaut to live aboard the ISS during a long-duration mission. Mission specialist Christina Koch holds a record that almost nobody talks about. She completed the longest single spaceflight by a woman in history, 328 consecutive days in space. She knows what 6 months of weightlessness does to your cardiovascular system, to your bone density, to your ability to stand upright the moment gravity reasserts itself. And then there is Jeremy Hansen, a Canadian Space Agency astronaut and the first Canadian ever to travel to deep space beyond low Earth orbit. When you put these 4 people together, you have thousands of hours of combined flight experience, hundreds of hours of spacewalking, and enough collective discipline to fill several lifetimes. And yet, for 7 minutes, none of that experience, none of that training, none of that accumulated human knowledge matters. What matters is whether a 3-inch shield holds, And that brings us to the part of this story that does not get nearly enough attention. During Artemis I, the uncrewed test flight that took the Orion capsule around the Moon, and back in late 2022, engineers discovered something deeply unsettling during the post-flight analysis of the heat shield. The avcoat material, 186 individual blocks of ablative ceramic arranged across a shield 16.5 feet in diameter, did not behave the way it was supposed to. Ablative heat shields work on a beautifully simple principle. As the capsule slams into the atmosphere at hypervelocity, the outer layer of the shield is supposed to heat up, char, and then systematically shed tiny particles, carrying the thermal energy away from the capsule's structure in a controlled, predictable manner. Think of it like a very controlled burn. The material sacrifices itself so that the aluminum and titanium beneath it and the human beings inside do not have to. But during Artemis I, instead of shedding in the fine, predictable way the models expected, the avcoat cracked. Not in small, insignificant ways, in ways that produced chunks significantly larger than predicted, chunks that peeled away in a pattern that no simulation had anticipated. When the engineers ran the thermal models, when they fed the data from the actual flight back into their equations, the models could not reproduce what they were seeing. The behavior was real, the physical evidence was undeniable, but the theoretical framework that was supposed to explain it simply did not account for it. Now, think about what that means. It means there is a failure mode in the most critical safety component on the capsule, a failure mode that exists in the real world but does not exist in the computer models that engineers rely on to certify the capsule as safe. NASA's response to this discovery was, depending on who you ask, either pragmatic engineering brilliance or a troubling shortcut. Rather than redesigning the heat shield, which would have required years of additional development and testing, NASA decided to change the angle at which Orion enters the atmosphere during Artemis II. By steepening the entry trajectory slightly, engineers believe they can reduce the aerothermal environment on the shield surface enough to prevent the anomalous cracking from becoming catastrophic. The computer models, the same models that failed to predict the cracking in the first place, now say that this modified trajectory is safe. Some NASA veterans are not satisfied with that answer. Charles Kamada, a NASA engineer and astronaut who flew aboard the Space Shuttle Discovery, and who was deeply involved in the investigation following the Columbia disaster, has been one of the most vocal critics of this approach. His argument, stated plainly, is that if you do not understand why something failed, you cannot be confident that your fix will work. You are not solving the problem. You are managing around a problem you do not fully understand. And managing around a problem you do not understand in a 7-minute window where there is no rescue, no abort, no second chance, is a very specific kind of gamble. The heat shield is not the only thing that has to work perfectly during those 7 minutes, not by a long way. Let us talk about the physics, because the physical reality of what the Orion capsule and its crew experienced during atmospheric entry is almost impossible to fully internalize. The capsule is traveling at approximately 11 kilometers per second when it first touches the upper atmosphere. 11 kilometers every single second. That is roughly 40,000 kilometers per hour, or about 25,000 miles per hour, depending on which unit feels more incomprehensible to you. It is approximately 33 times the speed of sound. It is fast enough to cross the entire continental United States in about 8 minutes. And this object, with 4 human beings inside it, is about to use the atmosphere of the Earth as a brake. When you decelerate something from that kind of velocity using air, the air does not simply get pushed out of the way politely. The capsule is moving so fast that the air in front of it cannot escape quickly enough. It gets compressed, violently and almost instantaneously, into a shock wave. And when you compress a gas that rapidly, it does not just get warm, it gets superheated. It ionizes. The electrons strip away from the atoms, and you end up with plasma, a fourth state of matter, a glowing, electrically charged cloud of superheated gas wrapped around the leading face of the capsule. The temperature of that plasma reaches approximately 10,000 degrees Celsius. The surface of the Sun, for comparison, is about 5,500 degrees Celsius. The Orion capsule, during entry, is flying through something hotter than the surface of the Sun. The heat shield surface itself reaches approximately 2,700 degrees Celsius, which is hot enough to melt steel, hot enough to vaporize many metals, hot enough that the word hot feels laughably inadequate. And the margin for error in the entry trajectory is measured in just a couple of degrees. If the capsule enters at too shallow an angle, it literally bounces. The atmosphere is not dense enough to grab it, and the capsule skips back out into space like a stone skipping off the surface of a pond. Except this stone has 4 astronauts inside, and there is no second chance, no more fuel, no rescue mission. They are gone, permanently. If the capsule enters at too steep an angle, the deceleration forces become lethal, and the thermal load on the shield exceeds its design limits. Somewhere between those two outcomes lies a corridor just a few degrees wide, and the autopilot has to thread the capsule through it with millimeter precision at 11 kilometers per second. The 12 small thrusters that control the capsule's orientation during this phase, 12, have to maintain the exact attitude of the vehicle against aerodynamic forces that are trying to tumble it in every direction simultaneously. If the attitude control system fails at the wrong moment, if the capsule yaws or pitches out of its optimal orientation by too many degrees, the heat load shifts to parts of the vehicle that are not designed to withstand it, and if that happens, there is no recovery. None. We need to stop here for a moment and think about what this means practically. Because there is a detail about these 7 minutes that I think gets underestimated even by people who follow space exploration closely. Once the Orion capsule separates from the European service module, which happens about 32,000 miles from Earth, the 4 astronauts are completely alone in a way that is almost unique in human history. The service module has been their power source, their propulsion system, their link to home in a dozen different ways, and it is gone, floating away behind them, never to be seen again. Now it is just 4 people in a metal capsule, watching the Earth get larger in their windows, with approximately 90 minutes until re-entry begins and no ability to change what is about to happen. And then, when the plasma forms around the capsule, something specific happens to their ability to communicate that I want you to really sit with. The plasma is electrically charged, radio waves are electromagnetic radiation, and an electrically charged plasma sheath of sufficient density physically absorbs and scatters electromagnetic radiation. It is not a software glitch. It is not a hardware malfunction. It is fundamental physics. The plasma literally makes radio communication impossible. For approximately 4 to 6 minutes, mission control in Houston goes completely dark. No telemetry, no voice, no data of any kind. The screens go blank. The specialists who have spent years preparing for this mission, who know every system on that capsule, who could in theory diagnose a problem in seconds if they could just see the data, are sitting in a room in Texas staring at nothing. They cannot hear the crew cannot hear them. Nobody knows in real time whether the heat shield is holding. Nobody knows whether the attitude control system is functioning properly. Nobody knows what is happening inside that capsule. Houston can only wait, and wait, and wait. And in those 4 to 6 minutes, the only thing standing between 4 human beings and annihilation is the engineering done years before this moment, the materials science, the manufacturing quality control, the software validation, and the decisions, good or bad, that were made about that cracked heat shield. If something goes wrong during the blackout, it goes wrong completely alone. The crew has their procedures, they have their suits, they have their training. But there is no voice from the ground to guide them, no second opinion, no real-time problem solving with a team of engineers. There is only what they already know, and what the capsule systems are still capable of doing. And meanwhile, their bodies are under a kind of assault that is hard to describe without having experienced it. Astronauts who spend extended time in space undergo profound physiological changes. The cardiovascular system, no longer fighting gravity to push blood from the legs up to the brain, begins to adapt. Blood pools upward. The heart shrinks slightly because it does not have to work as hard. The regulatory systems that control blood pressure become less sensitive, and then, in the span of a few minutes, those same astronauts go from 0 gravity to 4 times Earth gravity. 4G, 4 times your body weight. For a person who weighs 180 pounds on Earth, 4G means their body, in that chair, effectively weighs 720 pounds. Every movement of the head requires tremendous muscular effort. Every breath requires conscious work. The diaphragm, the muscle that drives breathing, is being compressed by the weight of the organs above it. The arms feel immovable, the face distorts. And this is all happening while the capsule is oscillating, vibrating, rotating slightly, as the autopilot makes continuous corrections, and while the crew is watching instruments and trying to assess whether everything's proceeding normally. NASA's preparation for this specific physiological challenge is detailed and methodical in ways that reveal just how seriously the agency takes the body's vulnerability during this phase. Before re-entry, the crew takes salt tablets, not as a casual supplement but as a deliberate medical intervention. Additional salt in the bloodstream causes the body to retain more fluid, increasing total blood volume. More blood volume means the heart has more to work with, which makes it harder for blood pressure to collapse catastrophically when gravity reasserts itself. They also wear compression suits, specifically the Orion crew survival system suits. These garments apply pressure to the legs and lower abdomen, physically squeezing the blood vessels in those areas and preventing blood from pooling in the extremities. They are, in effect, wearing a full-body tourniquet calibrated to keep blood in the chest and head where it needs to be. Without these suits, without the salt tablets, without the careful physiological preparation, the transition from weightlessness to 4G could cause blackout, not metaphorical darkness, actual loss of consciousness. 4 astronauts, unconscious, inside a capsule navigating itself through a plasma sheath at 40,000 kilometers per hour. That scenario is not theoretical. It is a real physiological risk that real engineers designed real countermeasures to prevent. And still, even with those countermeasures, even with the suits and the salt and the training, the body is under enormous stress during those minutes. Now let us assume the heat shield holds. Let us assume the attitude control worked perfectly. Let us assume the plasma clears and the blackout ends and mission control hears voices coming through their headsets again. You might think the danger is over. It is not, because now comes the parachutes, 11 of them, and they have to work in a specific mathematically precise sequence in a matter of seconds, and there is almost no margin for error. And if the sequence goes wrong at the wrong moment, the crew dies not in fire but in impact. The parachute system on Orion is one of the most complex recovery systems ever built. It consists of 2 drogue parachutes and 3 main parachutes, with additional smaller chutes involved in the deployment sequence. The drogues are deployed first, at a relatively high altitude and high speed. Their job is not to stop the capsule, which they cannot do. Their job is to stabilize it, to arrest any tumbling or spinning motion, and to slow it just enough so that the main chutes can deploy safely without being torn apart by the aerodynamic forces. The main parachutes, each one roughly 116 feet in diameter, are the actual braking system. When all 3 are fully deployed, they create a combined canopy area, enormous enough to slow a capsule weighing more than 20,000 pounds to a safe splashdown speed of roughly 17 miles per hour by the time it hits the Pacific Ocean off the coast of San Diego. But here is where the engineering gets frightening in its specificity. The deployment sequence is controlled by pyrotechnic devices, explosive cutters, small, precisely timed charges that sever the cables holding the chutes in their packs, as that cut the drogue lines at exactly the right moment to allow the mains to stream out, that release the main risers at the exact angle required to prevent line twists. Everything has to happen within fractions of a second of the planned timing. If a cutter fires too early or too late, the deployment sequence can cascade into chaos. A line twist at high speed can wrap the canopy into a useless bundle. A premature separation of the drogues before the mains are properly streamed can leave the capsule in freefall with nothing above it and no time to recover. NASA has tested this system with a ferocity that tells you everything about how seriously they take its importance. They have dropped full-scale capsule mock-ups from aircraft at altitudes above 30,000 feet and deliberately simulated failure scenarios. In one critical test, our engineers intentionally failed one of the 2 drogue parachutes and one of the 3 main parachutes simultaneously. They wanted to know not whether the system worked perfectly, but whether it worked at all under the worst realistic failure scenario. The answer, to NASA's relief, was yes. Even with 40% of the main canopy area missing, the remaining 2 main parachutes generated enough drag to bring the capsule down at a survivable, if harder than nominal speed. The crew would be bruised, the landing would be rough, but they would be alive. That test result is important not just as a technical data point but as a philosophy. The Orion parachute system was designed to survive partial failure and still save the crew. It was designed with the understanding that perfection cannot be guaranteed, and that the system has to function in an environment where something has already gone wrong. That is a profoundly different engineering mindset than the one that produced the space shuttle. where a failure of the solid rocket boosters during the first 2 minutes of flight left the crew with no options. None. The Challenger crew, 7 people, did not die in the explosion. The orbiter's crew module survived the initial breakup of the vehicle intact. The crew was alive. Some may have been conscious, but the module had no parachutes, no escape system, no mechanism of any kind to prevent it from falling from 73,000 feet and hitting the Atlantic Ocean at more than 330 kilometers per hour. The post-accident analysis suggests the entire crew could have survived the initial breakup. They died because there was nothing between them and the water. Orion was designed, in part, as an answer to that tragedy, as a declaration that the lesson of Challenger had been learned, and yet, even with all of these improvements, even with the parachute redundancy and the compression suits, and the blackout communications protocols and the modified re-entry trajectory, there remains a fundamental truth about those 7 minutes that no amount of engineering can entirely eliminate. If the heat shield fails catastrophically during the hypersonic phase, the crew dies. There is no escape from 10,000 degree plasma at 40,000 kilometers per hour. There is no ejection seat that functions in that environment. There is no technology that exists today, or that is likely to exist in the near future, that can extract a human being from a disintegrating capsule at those conditions and deliver them safely anywhere. The only protection against catastrophic structural failure during atmospheric entry is not failing, which is why the cracked heat shield from Artemis I matters so much, which is why the critics matter, which is why Charles Kamada and people who share his concerns are not simply being obstinate. They are making a specific, technically grounded argument that proceeding with a crewed mission using a heat shield whose failure mode you do not fully understand, and whose fix relies on the same models that failed to predict the original anomaly, is a risk that deserves more scrutiny than it has received. And yet, Reed Wiseman knows all of this, Victor Glover knows all of this, Christina Koch knows all of this, Jeremy Hansen knows all of this. These 4 people have read the failure reports, they have sat in the briefings, they have asked the hard questions, they have interrogated the engineers, they understand, with a clarity that most of us will never have, exactly what the risks are and exactly how narrow the margins are. And they got in the capsule anyway. Why? Why do people do this? Why, when you understand at the deepest possible level that there is a real, quantified, acknowledged probability that you will not come home, do you still choose to go? The answer is not simple. It is not just courage, although courage is certainly part of it. It is not just patriotism or duty, although those play their role. It is something harder to name, something that lives at the intersection of human ambition and human mortality, something that looks at the 7 minutes and sees not only the risk but the meaning. Consider what Artemis II actually represents. It is not simply a space flight. It is the first time since December 1972 that human beings will travel to the vicinity of the moon. For more than 50 years, a span of time longer than most people reading this have been alive, humanity has been confined to low Earth orbit. We have gone round and round, 400 kilometers above the surface, building stations and conducting experiments and demonstrating that we can survive in space for months at a time. But we stopped going anywhere. Artemis II is the first step toward breaking that confinement. It is the Pathfinder mission, the proof of concept, the demonstration that the systems work, that the trajectory is achievable, that human beings can once again travel through the deep black and return safely. And it will choose a trajectory specifically designed to allow a free return, meaning that even without firing a single engine, the gravitational mechanics of the Earth-Moon system will carry the crew home. The mission's designers baked survival into the orbital geometry itself, a lesson learned from the existential terror of Apollo 13, when an oxygen tank explosion left a crew stranded beyond the moon, and alive only because the trajectory allowed them to use lunar gravity as an escape route. Artemis II will not land on the moon. It will not deploy instruments on the surface or collect samples or plant a flag. What it will do is prove that we can get there and get back safely, and that proof, if successful, opens the door to everything that comes after. The eventual lunar landing, the permanent surface presence, the stepping stones toward Mars. All of that begins with these 7 minutes, if these 7 minutes work. And so when you ask why they get in the capsule, the answer is this. Because they understand that every great threshold in human history has been crossed by people who are willing to accept risk in the service of something larger than their own survival. The first people to sail out of sight of land did not know for certain that the Earth was round. The first people to fly in powered aircraft understood that the technology was untested, and the consequences of failure were immediate and fatal. The first astronauts who climbed into Mercury capsules and Vostok spheres and aimed themselves at orbit were doing so with computing technology less powerful than a modern calculator, trusting in engineering that had never been fully proven at the velocities involved. They went anyway, and the world changed because they did. Artemis II is not a mission to the moon, not yet. It is something quieter and in some ways more significant. It is a mission to prove that the path exists, that the systems are trustworthy, that the heat shield, cracked anomalies and engineering debates and all, can bring human beings home from deep space. 7 minutes, 2,700 degrees on the shield surface, 4G pressing 4 human bodies into their seats, 4 to 6 minutes of absolute radio silence, 11 parachutes opening in sequence over the Pacific. And on the other side of those 7 minutes, if everything holds, 4 people will be floating in the ocean off the coast of San Diego, Sossen, listening to the creak of the capsule cooling around them, feeling gravity for the first time in weeks, watching recovery divers approach through the hatch window. And the next chapter of human spaceflight will have begun. That is what those 7 minutes contain. That is the weight of them. That is why we are talking about them, and why they matter not just to engineers and astronauts and NASA administrators, but to all of us. Because if those 7 minutes work, we go back to the moon. And if we go back to the moon, the universe opens. And if the universe opens, it opens for everyone. Not just for the 4 people in that capsule. For all of us watching from the ground, from our screens, from our living rooms and classrooms and wherever it is we go, when we need to remember that human beings are capable of extraordinary things. The 7 minutes of terror are coming, and they are also, in the most profound sense, 7 minutes of hope. If you want to understand more about what makes deep space missions so brutally dangerous and so unbelievably inspiring, stay right here on This Is Space. We have much more to explore together. Thank you for watching.